So, as I said, and I will repeat, and then at some point I will repeat again, the nephron is the functional unit of the kidney. There are around 900,000 to 1,000,000 nephrons per kidney, and the nephrons are distributed radially between the cortex and the medulla. So the nephrons, are the functional unit, and they've got two main components. Okay, they've got the vascular components, which are blood vessels. The vascular component in the glomerular region is composed by by vessels vehicling blood under high pressure, so arterial blood. Arterial blood enters at high pressure the glomerulus, where it gets filtered. Okay, through large afferent arterioles, which then recombine to form a smaller outgoing efferent arteriole. Okay, so you've got the afferent arteriole, which opens up in the glomerulus and then converges in the efferent arteriole. Okay, afferent means going to, efferent means going from. Okay, from the Latin a and ex. The peritubular region has another vascular component characterized by venous blood under low pressure, which carries reabsorbed products to the renal vein and then the vena cava. The tubular region is the one that contains the filtrate, so to speak. So the proximal tubule arises from the Bowman capsule, also known as the glomerular capsule. The filtrate that forms in the Bowman's capsule that receives the high pressure blood from the afferent arteriole separates the bloody fluid due to the tight junction epithelial cells, which do not allow the leakage of fluid. And the tubular regions, so these tubes pretty much, contain microvilli or a brush border to increase the surface area for transport. So let's look at this glomerular region and the Bowman's capsule. Okay, so we do have, can I point things? I can't see how I can point things. There was this function for pointing at things, but I can't find it anymore. Yeah, I think I found it. Yeah, I hope you can see my pen. Yeah, okay, anyways. The arterial blood comes at high pressure through the afferent arteriole, entering the Bowman capsule. Okay, so this is the capillary tuft receiving high pressure blood and then converging again into the efferent arteriole. Okay, so of course the arterial blood entering high pressure, the Bowman capsule undergoes high pressure, and then it undergoes turbulent movement, and it gets filtered at high pressure. So on the side of the afferent arterioles, we have granular cells, and between the afferent and the efferent, we have these macula densa cells, which we will mention at a later point, and they're important. So between the capillary tuft and the Bowman's capsule itself, there are these podocytes, which are like the bricks in a wall. And between these podocytes, there are holes that allow the passage of the filtrate. So basically, the blood enters the capillary tuft through the afferent arteriole. It gets squished and filtered through the podocytes into the Bowman's capsule, and what goes from the blood into the Bowman's space is the filtrate, and then whatever is left leaves through the efferent arteriole. Okay, so this blood that gets filtrate through the podocytes, the basement membrane, the capillary endothelial cells, generate the filtrate. So the renal circulation, once again, contains an arterial high pressure component, which converges into the Bowman's capsules, and then a venal low pressure component, which is composed by the vasa recta around the lupovelle and ascending and descending limbs, which are involved in the reabsorption of anything that is secreted and reabsorbed through the nephrons. So the blood supply to the kidney is fundamental for two reasons. One, the kidney is a tissue like any other tissue. It needs blood to survive. Two, the function of the kidney is to filter blood. So, the function of the kidney itself requires constant supply of blood. If the blood circulation in the kidney is altered, for example, because of drugs or a disease, that can lead to kidney toxicity. I'm not going to enter into the details of blood vessel structure because this is something to cover in other lectures. So look at them if you want to know more about this detail, or just drop a question in the Padlet. Okay, so the blood supply to the nephron, as we said, is characterized by afferent and efferent arterioles, which are important for the filtration process itself. But then the efferent arterioles from medulla form the vasa recta, which supply with blood the medullary regions and drain into arcuate veins. So I've already kind of mentioned how in the Bowman's capsule and in the glomerulus occurs the process of filtration. Now, filtration is only one of the three processes that occur in the nephron. Filtration occurs in the glomerulus, is basically the filtration of the plasma of the blood which enters the tubules. But then within the tubules, we do have reabsorption of substances that are filtrated, and they shouldn't have been filtrated. No, I'm joking. Everything that is filtrated needs to be filtrated, but then some of these substances are reabsorbed, while other substances that are not being filtrated but need to be excreted get secreted from the blood into the tubules. So the filtration process occurs because of the difference in blood pressure at the afferent arteriole and the other tissue. Of course, for the filtration process to occur, the pressure in the afferent arteriole and the capillary shaft has to be higher than the pressure inside of the Bowman space. So the forces that drive this process are Starling forces. During the filtration process, ions, water, and small molecules are removed from blood, and as you see, other substances that we need to be reabsorbed. And the rate at which the kidneys form the ultrafiltrate or the first filtrate is known as the glomerular filtration rate, which is the rate at which the blood is filtered in the glomeruli, and it's measured in milliliters per minute. So once again, the afferent arteriole brings the blood in. The Starling forces promote the filtration of the plasma through the podocytes and the basement membrane, the capillary endothelial cells. And many substances, including electrolytes, water, and more substances that we will look at some point, will form the filtrate. So the Starling forces are mostly characterized by two components: osmotic forces and hydrostatic forces. Okay. So we will have obviously glomerular hydrostatic pressure, which is basically due to the hydrostatic pressure of the arterial blood entering the afferent arteriole. And the direction of this pressure will be from the artery, from the capillary to the Bowman space. Then we will have osmotic pressure, which is due to the difference in concentration of solutes between the Bowman space and the plasma. And of course, the plasma will have a higher osmolarity than the filtrate. So the total resulting colloid osmotic pressure is of 32 millimeters of mercury from the Bowman space into the capillary. And then finally, there is the hydrostatic pressure within the Bowman's capsule, which is of 18 millimeters of mercury. So it's easy. You have to do 60 minus 32 minus 18, and you will know the net filtration pressure, which will always be directed from the arteriole to the Bowman's capsule. Of course, if the hydrostatic pressure drops below the sum of 18 plus 32, then you don't filtrate blood anymore and you're in trouble. So the filtration membrane has three main components, which I've quickly passed through. The first component is the capillary endothelium, which has large pores. You know, the endothelium of the capillaries here is much more permeable than the endothelium in any other part of the body. It has such large pores that are called fenestrations. Finestra in Latin means window, which increases the permeability. Okay, normally endothelium is a barrier. It obstacles filtration. Okay, so this is still going, yeah? Yeah, sorry, sometimes my computer does weird things. So normally the endothelium is a barrier, okay? While the role of this endothelium in the glomerulus is to actually allow filtration, right? So it's a particular kind of endothelium with large solutions of continuity between one cell and the other, so large pores called fenestration, increasing permeability. Basement membrane, so again, very porous and negatively charged like proteins, and that's the main site of filtration of proteins. And then, of course, the Bowman's capsule and the epithelium itself. Bowman's capsule is tube, which is covered by endothelium. These are called podocytes, and they extend pedicels to form filtration slits. So it looks more or less like this, yeah? So we go from the lumen of the capillary, where the blood comes with high pressure, 60 millimeters of mercury, and then we have this atypical endothelium. Yeah, this is the glomerular endothelium, which has these large pores called fenestrations, which we don't have in other parts of the body. And then we do have this basement membrane between the capillary endothelium and the Bowman's capsule endothelium, epithelium, which is negatively charged. And then the Bowman's capsule epithelium has spaces between one cell and the other, known as filtration slits. Okay, so the filtered material goes through these solutions, interruptions of continuity of these two barriers, the capillary endothelium and the Bowman's capsule epithelium. And then you see the different composition of the plasma and of the filtrate, okay? So if the ratio between filtrate and plasma is 1, it means that that substance is equally contained in the plasma and in the filtrate. So water, urea, glucose are all freely filtered. Glucose, interesting. Glucose is filtered. Glucose goes entirely from the plasma to the filtrate. Okay, remember this, because if you remember, we said that urine should contain 0 glucose. And if you have more than 0 glucose, that may be a sign of pathology. But now we're seeing that the Bowman's capsule, the glomerulus, filtrates glucose. So glucose goes from the plasma to the filtrate with no obstacles. Inulin gets largely reabsorbed, and then proteins, reabsorbed. It's almost completely filtered through, and then proteins can also be filtered through, but the higher is the molecular mass, the lower is the fraction of protein that gets filtered. So as you can see, there is a direct relationship between the molecular mass of each one of these substances and the ratio between filtrate and plasma concentration. Meaning that our limit is glucose. Anything above it, or anything in the region of kilodaltons, starts to be not filtered anymore. Albumin virtually doesn't pass through. Hemoglobin virtually doesn't pass through. Okay, but here we are in the tens of kilodaltons. Very important. Remember these. Right. So once we have filtered the plasma into the Bowman space, we will have a filtrate. This filtrate will contain water, electrolytes, and glucose. Also, a portion of proteins, if they are small enough to go through. Myoglobin could go through quite effectively, as a matter of fact. There's not myoglobin in the blood, though. Now, there are two other processes: reabsorption and secretion. These are extremely important processes for conserving electrolytes and regulating osmolarity or osmolality. Okay? So reabsorption, remember, is the movement of substance from tubular fluid to the blood. Okay? Again, reabsorption is the movement of substance from the tubular fluid to the blood. For example, potassium and urea. While secretion is the movement of substance from the blood into the tubular fluid. Okay? So reabsorption goes from the blood, from the tubular space to the blood, while secretion goes from the blood into the tubular space. Okay? What is clearance? Clearance is the rate at which a compound is removed from the body. For example, is excreted in the urine. So it's a very general term. And it's equal to the volume of plasma completely cleared of that substance in 1 minute. So clearance is equal to the concentration of that substance in the urine divided by the concentration of that substance in the plasma times the rate of urine production in milliliters per minute. How do you calculate that? Let's look at glucose. Glucose, as we know, gets entirely filtered through from the plasma into the Bowman space. So if I have, for example, a concentration of glucose of 700 milligrams per minute entering the glomerulus, and then we have, a concentration of, this 700 milligrams per minute is equal to the concentration of glucose in the plasma times the renal perfusion rate. The filtered load will be equal to the plasma concentration of glucose times the glomerular filtration rate, so 100 milligrams per minute. Now, glucose, and this is very important, you need to remember it, gets completely reabsorbed. Okay, well, at least in a working organism. So if the filtered load is 100 milligrams per minute, the reabsorption of glucose is 100 milligrams per minute. So the concentration of glucose in the urine is 0 mg per minute. And for simplicity, let's say that the renal perfusion rate, in this case, the V is equal 1. Now, in this second example, okay, we have a concentration of glucose which is 5 mg per milliliter. Okay, so this person has hyperglycemia. So we do know that in physiological conditions, 100 milligrams in 100 milliliter of blood of glucose, 100 milligram of glucose in 100 milliliter of blood is the physiological concentration, right? So instead of having 1 mg per ml, we have 5 mg per ml, for example, in a person with diabetes. Again, we will have the glucose freely moving from the blood into the filtrate. But then at some point, my reabsorption system will be saturated. So if my filter load is equal to the plasma concentration of glucose times the glomerular filtration rate, which is equal to 500 mg per minute, but then my reabsorption is only 375 mg per minute, because that's the limit of my reabsorption rate, because the kidneys are not made for reabsorbing all that amount of glucose, then my urine levels of glucose in time will be equal 125 mg per minute. Now, this is important because if I look at the clearance of glucose in physiological condition, I will see that the clearance of glucose is 0. And that's important because I don't want to clear glucose. But if my clearance of glucose is not 0, that may be a sign of a problem. In this case, the problem is the hyperglycemia, or it may be some renal disease which impairs reabsorption. In any case, is a sign of a problem.